So thank you for the organizer for inviting me and giving me this great opportunity to talk here. I'm very happy to be here. So today I'll present some work I've done on information extraction, but I'll also try to present some kind of where is the field right now and what are the big challenges about information extraction. So very briefly, what's information extraction? So the goal is to extract structured information from unstructured documents. So for example, to build a knowledge base from free text or text in human language. And so one of the obvious motivation for this kind of information extraction is to be able to answer to that kind of query. And so to be able to know that the population of Los Angeles, for example, is a bit less of 4 million people, and it's in the US, and all those stuff. And so now I'll give some example of some specific example of information extraction. So the first one is just to extract named entities, such as the name of location or the name of person from human language text. And so traditionally in NLP, people have been trying to have been working on data sets which focused on three kind of named entities, which are people, location, and organization. But depending on what domain you're working in, those named entities can be a lot of different things, such as genes, cells, proteins, if you're working in the biomedical domains, laptops, name of laptops, phones, camera, if you're trying to extract those kind of things, I don't know, from Twitter or whatever. So a second important thing to do is to be able to, once you've extracted those entities, to link them into a knowledge base, for example. And because a lot of those entities are very ambiguous, for example, Michael Jordan, so of course he's the very famous basketball player, but he's also a very famous professor of machine learning at UC Berkeley, and you don't want to mistake those two person when you're extracting information about them. And so finally, you'd like to be able to extract relations between those named entities. So for example, in that sentence, you have a bunch of entities again. And so the kind of relation that you'd like to extract is the fact that Alan Turing was an employee of the Government Code and Cipher School, or the fact that this school was located at Bletchley Park. And most state-of-the-art methods for information extraction are based on supervised machine learning. And so in the last 15 years, there's been a lot of advance in information extraction thanks to these techniques. But they still suffer from, I think, quite limitations. The first one is obviously the fact that you need labeled data, which is often quite expensive to obtain. And in information extraction, this is really a problem because you have really 1,000 different kind of entities or relations that you'd like to extract, and you can't reasonably label data for all those kind of entities or relations. The second thing is that if you want to develop, for example, a product and you'd like to make this product available for different languages, you don't want to annotate data for each new language you want to support. Another limitation is the fact that it's not robust at all to domain shift. And so this is an example of a sentence that's extracted from a financial report about a healthcare company. And so Henry Schein is actually an healthcare company, and so given the fact that it appears in that particular document, it's much more likely that this is referring to the company than to a person, but a named entity extraction system trained on general data will always label this as a person, and actually it makes sense. I mean, without knowing that this sentence is extracted from a financial report, most of you would say that Henry Schein is actually a person. So now I'll present two of in more detail two of these problems. So the first one is the relation extraction. And so one of the things people have been working on to not rely on labeled data is to actually use an existing knowledge base instead of labeled data. So for example, you can consider this very simple knowledge base with two facts, two named entities. And so then you can extract named entities from unlabeled data, link them to the knowledge base, and then label each of these sentences using the relation that appear in your knowledge base. So, of course, the problem with that approach is that the labeled data that you obtain is very noisy, because a lot of the named entity pairs can verify, for example, several relations. So you have to be able to say which sentence express the fact that Liechtenstein was born in New York City, and which one expressed the fact that Liechtenstein died in New York City. Another thing is the fact that many of those sentences actually doesn't express any relation you are interested in, and so you don't want to label those sentences as expressing one of the relation. And so one of the solution for this problem is to view this as a multiple instance, multiple label learning problem. So multiple instance because for each entity pair you'll have a lot of sentences. So those are your multiple instances. And for each pair of entities, you want to be able to predict a lot of different relations. And so some very quick notation. So for the rest of this part, xn will be a vector, a feature vector that will represent each sentence. And so we suppose that we have k different relations, and so we have a matrix Rik that will tell us if the entity pair I verifies the relation K. So basically this is the information that is in the knowledge base. And we have a second matrix E such that EIN is equal to 1 if the sentence N, and in particular the pair of entities appearing in sentence N, is linked to the pair of entity I. And so basically this is the information, the data linking, the linking part, the entity linking part. And so what I will present now is a way to infer for each sentences the actual relation that is expressed in that sentence. And so once you have been able to infer those labels, you can just train a regular classifier because you have, in that case, regular labeled data. And so the goal is to infer a matrix Y such that Y and K is equal to 1 if the sentence N express the relation K and 0 otherwise. And so the approach I will describe is based on discriminative clustering that I will now rapidly introduce. So the idea of discriminative clustering is, let's say that we have a set of data points, and you would like to cluster them into two groups. And so the criterion that will be used to say that a clustering is a good one is there exists a good classifier separating these two group of points. And so basically what discriminative clustering is trying to find is a set, so two groups of points that can be very easily predicting using discriminative algorithms such as an SVM or a logistic regression. So basically, this means that if you have a loss function L, such as the hinge loss or the logistic loss, and a given regularizer omega, the goal is to find a matrix Y and a classifier F, minimizing the empirical risk. And so the good thing about this approach is that we can very easily put the information we know about our data by putting some constraint into Y. And so basically what we'll do is that we'll use the supervision obtained thanks to the knowledge base by defining some constraint on Y. So the first constraint is that we suppose that each sentence expresses exactly one relation. And so basically what does that mean? It means that the line on the line of the matrix Y, there should be exactly one. And so we could rewrite this as, because Y is a binary matrix, as the fact that the sum over the line should sum to 1. The second constraint is the fact that if, again, according to the knowledge base, an entity pair I verifies a relation K, then we suppose that we have at least one sentence in our data set that will express that fact. And so basically, what does that mean? So I remind you that EIN is equal to 1 if the sentence N corresponds to the entity pair I. So this means that for all the sentence in which the entity pair I appears, so basically for all the sentence N such that EIN is equal to 1, we want at least one of the corresponding Y and K to be equal to 1. And so basically, again, we can write this as taking the sum over all the sentence that in which the entity pair I appears, and taking the sum over all those sentences, we want these sums to be greater than 1. And so we can rewrite this like that, and so we obtain a linear constraint on the matrix Y. On the other hand, if an entity pair I does not verify a relation K, then we suppose that no sentences in our dataset express that relation. So basically, that's kind of a strong constraint, because it supposes that the knowledge base is actually complete, that there's no missing information in the knowledge base, which of course is not really true. But that's not that big of a deal, because first, for most relations, this is actually true. And you could actually only consider, when building a dataset, the named entities that you think that you have most of the information. For example, named entities that are very common, such as Barack Obama. I mean, for example, the children of Barack Obama are obviously all already in the knowledge base, and so there's no missing information in that case. And so again, we will consider exactly the same kind of constraints. So except that in that case, instead of forcing the sum to be at least equal to 1, we want all the elements of that sum to be equal to 0. And so this is equivalent to saying that the sum should actually be equal to 0. So this is very similar to the previous constraint. And so finally, a small technical constraint. We suppose we don't want to put too much to classify too many sentences as the non-relation, and so we just impose that at most a certain percentage of those will be classified as other or none. And so again, you can write this as a linear constraint on the matrix Y. And so this constraint can be rewritten in that way. And now so first, is there any questions so far? Okay. This one? That one? Okay. So basically, the first one is just saying that the sum over the line is equal to 1, and the second one is just rewriting the three other constraints by introducing one matrix S. But this is not really important. Any other questions? Okay, so now I will go back to the discriminative formulation of that problem. And so in that case, we'll use the first linear classifiers and the squared loss. So the square loss is not a classification loss, so that's a bit strange to use that loss instead of the hinge loss of the logistic loss. And so the reason for that is the fact that that formulation is actually, this loss function is actually jointly convex in Y and W. So this problem, and we can obtain a closed form solution for W. But so in this problem, everything is convex except for the constraint that Y should be a Boolean matrix. And so replacing W by its optimal value, we obtain a problem that is a quadratic integer program. And so this is, in general, this is NP-hard. This is an NP-hard problem. But again, there's only this constraint that's non-convex. And so the very natural thing to do is just to relax this constraint into the fact that the y's should be into the between 0 and 1. And in that case, we obtain a convex quadratic program, which can be solved by any solver such as Mosaic or anything, and it's actually very easy to solve. The other interesting thing about that formulation is the fact that it only depends on the kernel matrix XX transpose. And so basically, instead of taking linear classifier, you could use any, you could use any kernel that you want. And actually, in the field of relation extraction, a bunch of kernel based on dependency trees have been used, and so it would be possible to use this kind of kernel in that case.
So the relationship of X to its transpose is representing that as a linear classifier.
So
I'm still having a little bit of problem keeping in my mind all the single letter variables. So Y is the original entity pair.
So Y are the latent variables,
Right.
yeah.
And then X corresponds to
And X corresponds to the vector that will describe each one of your sentence. And so basically, you're trying to predict Y using just a regular dot product between W and X. Yeah. Okay, so of course, since we've relaxed the problem, the solution we'll obtain is not an integer solution. And so one solution to obtain an integer solution is actually to project to take the orthogonal projection of the matrix Y star, the optimal solution of the relaxed problem, onto the set of indicator matrices. So in that case, when doing this kind of rounding, you don't necessarily obtain a solution of that will verify the original um, constraints, but in practice it works really well. But there's no guarantee that the solution obtained in that way verifies the original constraints. And so using this Y, you can then just train a regular multi-class classifier to learn to extract relation. So a very quick word about optimization. So in that case, it's actually easier to solve the dual than the primal problem, because in the primal problem, you have this matrix inverse, which is kind of a problem, because if you have millions of examples, this matrix XX transpose plus lambda IN is actually a million times a million, so it's a very large matrix, and it's not necessarily easy to compute its inverse. But actually in the dual, you get rid of this inverse, and moreover the constraints are much simpler, and so it's very easy to project on the constraint. And so it's possible to use an accelerated projected gradient descent algorithm, sometimes referred to as FISTA. And so the overall complexity of this optimization algorithm is of one iteration of this algorithm is O of NFK, where N is the number of sentences, F is the average number of features used to describe a sentence, and K is the number of classes. So now I'll briefly present some experiments. So the experiments were carried out on the dataset made of articles from the New York Times. So the entities were extracted using an off-the-shelf named entities recognizer, and they were linked to Freebase using a very simple heuristic that's just a string match. So there's actually quite a noise coming from there. And so there's 52 relations, 4,000 entity pairs, and 100,000 sentences. So n is equal to 120,000 in that case. And so as the features are built as follow. So we considered lexical features such as the sequence of words between the two entities, the word that will appear before the first entity and after the second entity, the part of speech of this word. We also consider syntactic features such as the dependency pass, the pass in the dependency tree between the two entities, or the neighbor of each entity into the dependency tree. And so one of the first, so here is results and comparison to other methods. So the first one is the things I described at the beginning of the talk, is just to heuristically label each sentence using all the labels that you can get into your knowledge base. So of course there's a lot of noise, but still it's working working a bit in practice. Then these are two methods based on latent variable model, and which actually are not convex and kind of suffer from the initialization you're using. And so here is the method I've just described. And so obviously it would be interesting to try to initialize the previous model using the method that I've described, which I haven't done yet. And so here are the results for different kind of relations to show you that it's working quite well for certain kind of relation, such as the fact that a location contains another location, or the fact that a person is working for a company, but it's not working very well for other kind of relations, such as the fact that somebody was born in a certain place, or the fact that a person have lived in a place. And I think that's just because this information is actually not present into the New York Times article. And so finally, here are the result for classifying at the sentence level. So that's the for each sentence saying which relation is expressed by the sentence, while the previous results were for each entity pair saying which are the relations that are verified by that entity pair. So any question on that? Yes.
When you originally set the C parameter,
Yes.
only ignore a small portion of the data set. When this flows through, is there any danger of overfitting later on or fitting to the noise?
That's a good question, and I don't know because I haven't really tried to see what happens when you. So basically, I cross-validated this C parameter, but I don't know what happens, for example, when you go from a complete, for example, if new entity appear, then you don't have any information about those entities in your knowledge base, and so maybe the C wouldn't be the same, and some kinds of things like that. So I don't know. Any other question? Okay, so now I'll talk about named entity classification. And a particular problem, which is extracting named entities from technical text, such as financial reports. And so I think that the current state of the art is not really a good way to address this problem. First, because again, for most of the technical domain, you don't have labeled data. Second, because there's this domain shift, and so even if you just want to extract, for example, the name of organization from financial reports, a system trained on general on text from general domain is doing actually very poorly on technical text. And actually, there's one more interesting thing, is that for many domains, these named entities are actually not ambiguous at all. And so you don't need to have something as a classifier that is as fancy as the things that are currently the state of the art, because since the named entities, many named entities are not ambiguous, the problem is much easier than for general domain. And so an old idea for training a named entity extraction system without labeled data is to start from a seed list. So for example, a small list of companies, and to try to match those named entity to unlabeled text, and then to obtain some kind of labeled example, so that you can extract, for example, pattern that will allow you to extract new named entity from your unlabeled text, and then you can iterate this process to grow the set of named entities and grow the set of pattern, and in the end be able to extract most of these named entities.
So is that bootstrapping to sort of identify
Yeah, but that's really, maybe that's not a very good example, but yeah, that's for extracting named entities. And so, for example, one other pattern could be the fact that you'll have the token Inc. After the name of companies.
Okay, so out of this, you're able to then sort of generalize
Yeah,
some pattern.
exactly.
Okay,
And so one of the limitation with this scheme is the fact that you can rapidly have a lot of noise into your list of named entities. And once you're starting to make some small mistake into the entities you're extracting, very rapidly this can go completely out of control, and you'll end up with extracting something really different than what you intended. So here, what I propose is to do something slightly different. Is again to start in the same way, so with a seed list of named entities, to extract to try to match all the elements of this seed list into unlabeled text, to obtain a positive example. And because, again, we assume that the named entities are not ambiguous, those are really positive examples. And then you can try to train a classifier using those positive examples you've extracted. And but you will not iterate between extracting entities, training a classifier, extracting more entities. You really want to train the classifier at once. And so, but the problem in that case is that you don't have negative example. You only have positive example, the thing that you've been able to match into your to something that appear in your seed list, and all the other potential named entities are actually unlabeled example. And so this is an example of something that's referred to PU learning in the machine learning community, which is learning from positive and unlabeled example only. And so now, basically, I'll show that this problem of learning from positive and unlabeled example is very similar to what I've presented in the first part of the talk, and the same kind of tool can be used. So again, very quick notation. So the vector x in that case are a set of features that will describe each potential named entity, and so the text surrounding this potential named entity. So P is the set of positive example, U is the set of unlabeled example, and so we suppose that we have a bunch of label for the positive example, and again we allow to we have a label other for all the things that are not actually named entities. Again, the goal will be to infer a binary matrix y and k such that y and k is equal to 1 if the mention, the potential named entity mention n is actually of class k, and 0 otherwise. And so basically what's changed to the previous problem is the kind of constraints that we'll put on y. So again, we suppose that each named entity belongs to only one class. So that's the equivalent of the fact that each sentence can express only one relation. So again, y should sum to 1 on the line. Of course, for the positive example, we want the matrix y to agree to what we've obtained using the seed list. So y of n cn should be equal to 1. And so finally, since we don't want all the example to be classified as one of our potential class, we'll impose that we have at least a certain percentage of the example to be classified as other. And so again, we'll have a parameter p in that case, saying, okay, I want, I don't know, maybe 50% of my potential named entity to be classified as other. So are there any questions on those constraints?
Is that percentage literally that high when you're talking about 50% or something?
I guess it really depends on the data set you're considering. So again, we can formulate this using linear classifier and the squared loss, and we obtain a problem that's very similar to the previous one, except that the constraints on y are a bit different, but again, that's still linear constraints. So we still obtain a quadratic integer program. And again, we'll relax the fact that the matrix y should be a bit binary matrix into the fact that y should be, the y's should be between 0 and 1. And we obtain a problem that, again, is jointly convex in y and w, and so can be easily solved with any of the shelf quadratic solver. So this is pretty much work in progress. So the data set considered for this problem is a bit of a toy data set. So the goal is to extract name of companies and name of drugs from financial reports corresponding to a healthcare company. So as the seed list, we've considered the name of publicly traded companies, the 200 most searched drugs on the website, on a website listing all the drugs that are sold in the US, and as feature, so we use the tokens that appear in the entity mention, the word that appear before and after, again the ancestor in the dependency tree, and the vectorial representation of the mention, a word embedding of the mention. And so here are the results. So the first one, the Stanford NER, is a state-of-the-art named entity recognizer system that was trained on general domain. And so what we see is the recall for that system is very low on those dataset, because, for example, Aspen will always be classified as a location, or Merck is often classified as a person, and things like that. The second one is the string match, to show you actually in that case the named entities are really not ambiguous, and so we have precision that are almost 100%, and that the recall is actually not that bad. As I was quite surprised that it was so high. And so the last one, the SVM, so is just training an SVM with asymmetric cost for the positive example and the unlabeled example, which is something that's worked quite well for PU learning. And so finally, the method that I've presented, which obtain results which are very similar to the asymmetric SVM. And so here are some curves to show the influence of the parameter P. So when the parameter P increase, we'll tend to classify more and more potential named entities as other, and so the recall will drop, but the precision will augment. And so that's what you can observe here. And so actually that's a way to choose the precision or the recall of your classifier.
Sorry, just on that diagram, the axes are P against, the axes themselves are representing P.
So this is P against the precision, the recall, and the F1 score of the classifier. So do you have any question? Yes. That's a good question. Actually, for this experiment, there's only one classifier that is trained, a multi-class classifier that is trained, and so the P is the same for the two classes. And why does the effect is different? I don't know. Yeah.
Is the effect related to the number of seeds because you seeded
Yeah, that's
with way more than drugs?
that can be a reason. Another reason could be the fact that one class is more frequent than the other. Another reason could be the fact that drugs maybe appear in simpler patterns to extract, and I haven't really tried to know why it was different. But actually, yeah, the good thing is the optimal P is almost the same for the two classes, and actually it almost corresponds to the actual percentage of mention that should be classified as other. So that means that you could actually set, if you know the percentage of named entities that should be classified as other, you can set P that way, at least on that data set. Yes. So you either need a test set, or again you can also just try to know the percentage of things that's classified as other, but which is actually much easier to obtain that label data, because you can just take maybe a couple of sentences and just roughly compute how many of your examples are actually other, and you don't have to label each of the positive example into one class, or even have one example for each of those positive class. So that's easier. And if you want, of course, if you want to cross-validate P, then you'll need label data. So to conclude, so I presented a method for learning to extract information using distance supervision, which is based on discriminative clustering. So that leads to a convex formulation that's quite easy to solve in practice, and it seems to be quite competitive to other techniques for information extraction in the distantly supervised setting. Again, this is pretty much work in progress, and so there's some different things that I am working on or I'd like to work on. The first one is to develop faster optimization method for this approach, because this couldn't scale for right now to millions or tens of millions of example, or to millions, or to thousands of relation. The second one, which is quite related to the first one, is how to kernelize those method in practice, because when for kernel methods, you have this giant kernel matrix to compute, which is actually n by n, where n is the number of example, and so in that case it's not trivial to do. And so finally, I'd like to consider more challenging data sets for the named entity classification task, and in particular data sets in which the named entity are ambiguous, because it's possible using the same framework to consider such entities. So if you're interested in more details, there's those two papers that describe the thing. There's code on my webpage, but that's research code, so it's very specific to the data sets and everything that's described in those articles, so it's not really usable in practice. and I might try to release general code for that program in the future. And thank you for your attention, being here, and inviting me.
Okay, and any questions left? Yeah, we have one question. Yeah, microphone.
You compared several different methods. Is it possible to generalize it and say what the computational complexity is, the number of operations, or some other way to talk about the different methods and get a feeling for the, let's call it speed accuracy trade-off?
So, which methods actually? Okay, so for example, so the first one, so it's just training a multi-class classifier, the orange one. So that's super fast, and that actually kind of the fastest thing you can do. And so then in the two other methods, so there's one that's really fast because they're relying on approximation tricks, and so it's actually almost as fast as the first one, while the other one is a pretty complicated latent variable model where the inference is complicated, and so it's actually slower than slightly slower than the method I presented. I don't know if that answers your question. Oh, so on, for example, on this data set, so again for 50 relations and 100,000 example, I think that the very naive method is something like of the order of a minute or a couple of minutes. The fast latent variable model is also like maybe 10 minutes. The two other one is the order of hours.
Any other questions?
Do you have any general insights on how to deal with the problem that you need a test set for evaluation?
No. So actually, how this is a good question. How this is evaluated? So this is actually evaluated on Freebase, and so this is not the actually precision and recall of this method, because Freebase is incomplete, and so you'll actually extract facts that are not in Freebase yet, and so when you evaluate, you'll say, oh, this does not appear in Freebase, so this is a false positive. And actually, the problem is I don't think there's a good way to evaluate when you want to train such method on large number of relations, because you cannot. So you can either label data for a subsample of relation, or rely on something like using an existing knowledge base, or there's a way to evaluate the precision of your classifier by taking, for example, the couple hundred of thousand of extraction and actually say if it's a correct extraction or not. But you cannot evaluate the recall that way. So there's no. I think there's no good way to evaluate.
You also gave like a sentence level
Yeah.
precision recall. So did you also do that only using Freebase, or how do you do that?
So this was a couple of sentences, 1,000 sentences, I think, were hand labeled, and so you just take the classifier that you've just trained, you run it on those sentences, and then you can, since you have the label for each sentence, you can evaluate the classifier.
Last
Is the approach of, in the algorithm itself, minimizing with respect to both y and w, is that dependent upon these convex relaxations, or can other techniques use minimization of both variables at once?
So there's lots of way to do that. The first one of the thing that you could do is something like EM, for example, and so to alternate between the optimization on Y and on W, and keeping the Y integer. You can also consider other kind of convex relaxation, more complicated convex relaxation, like SDP relaxation and things like that, which usually give better results. But in that case, that's kind of complicated because of the constraints that appear. I don't know any other techniques.
Thank the speaker again.